Hi, I am Andy Myers, and in this video, I will be discussing quantum dot solar cells. I will go over the motivations for researching quantum dots, provide a technical overview, and discuss current technologies and their limitations. Photovoltaics as a whole are a popular form of renewable energy. One reason is the theoretical potential. The amount of solar radiation that reaches the Earth's surface in about an hour and a half is enough to power the planet for an entire year. Of course, there are many limitations to this, the most obvious being the sheer infeasibility of covering the planet in solar panels. But this represents the enormous amount of free energy that could be harvested by engineering smart solutions. Photovoltaics are also already popular, with many companies offering installation and world governments subsidizing construction. People are generally supportive of the use of photovoltaics, which will likely continue into the future. Last, photovoltaics can be useful in remote generation. Rural villages can use solar panels to provide electricity without setting up an expansive grid system. Furthermore, photovoltaics can be used to supply energy to spacecraft on long-range missions. The way most photovoltaics operate is with a p-n junction. Doping a semiconductor with other elements will make the semiconductor more conductive. In semiconductor physics, a p-type material is one with dopants that create more positive carriers, which we call holes. An n-type material, on the other hand, adds more negative carriers, or electrons, to the lattice. These carriers reside in either of two energy levels, the conduction band or the valence band. The energy difference between these two bands is referred to as a band gap, and many properties of a material depend on its band gap. Electrons in the valence band are bound to an atom, but when they are in the conduction band, they are free to move about the lattice. When a photon of sufficient energy is absorbed, an electron can be excited from the valence band to the conduction band, so it will move through the lattice. This electron diffuses until it either recombines with a hole and goes back to the valence band, or it reaches a metal contact and is able to leave the semiconductor. The electron travels through this external circuit, generating power before it returns to the semiconductor. This process is how most solar cells generate power. A common theoretical efficiency limit for solar cells is known as the Shockley-Queisser limit. One of the principles underlying all of quantum mechanics is that energy is quantized. Light comes in discrete packets called photons, and a single photon can excite a single electron. This can cause problems for photovoltaic applications. The sun is a black body, so it emits radiation across a wide spectrum. A material absorbs light most efficiently when the light has the same energy as the band gap, but solar cells encounter wavelengths across the solar spectrum. This leads to the Shockley-Queisser limit, which determines the theoretical power conversion efficiency of an ideal solar cell based on the band gap. When a photon with more energy than the band gap is absorbed, some of the energy is lost to thermalization. When a photon of energy less than the band gap is incident on the material, it will not be absorbed and energy is again lost. Taking these energy losses into account, even a material with the band gap most suited for the sun's radiation can't convert more than 33.7% of the incident radiation into energy. This calculation also assumes some idealities in the semiconductor, so real efficiencies are even lower. To make better solar cells, most research is focused on finding ways to surpass the Shockley-Queisser limit. Quantum dots offer a few ways of going about this. So what exactly is a quantum dot? Quantum dots are tiny particles of semiconductor with sizes on the order of a few nanometers. They are typically suspended in solution and exhibit different properties than the bulk material. The first paper on quantum dots was published in the early 1980s by a Russian physicist named Alexei Ekimov. He observed that quantum dots of different sizes fluoresce different colors, a property that is determined by the size of the band gap. Not long after, two British scientists identified that the unique properties of quantum dots could be used to achieve higher efficiencies in solar cells. It is also easier to synthesize a quantum dot than it is to fabricate a solar panel. So they could be advantageous in terms of cost too. Making silicon solar panels is an energy-intensive process and requires delicate balance. Quantum dots are usually solution-based, so they are easier to synthesize and deposit onto a substrate. The main reason quantum dots are so interesting for solar applications is that they have a tunable bandgap. This is advantageous over traditional silicon PV because silicon has a fixed bandgap of 1.1 eV. This is a good bandgap, but 1.3 eV is ideal according to the Shockley-Queisser limit. Quantum dots have the flexibility to be adjusted to suit the incoming radiation. This property is due to quantum confinement. Essentially, as the dots get smaller and smaller, the electronic structure starts to become more like a single atom. Energy levels become more quantized, and the bandgap becomes larger. This behavior can be explained by solving the Schrödinger equation for a particle in a three-dimensional box, as we did in a homework assignment earlier this semester. First, we write out the time-independent Schrödinger equation and assume the potential is 0 inside the box and infinity outside the box. The particle cannot exist outside the box, so the Schrödinger equation must be 0 at the edges of the box. By applying these boundary conditions and assuming the overall function can be separated into its x, y, and z components, the eigenfunctions are shown to be in the form of a three-dimensional sinusoid. From these functions, we get these eigenenergies. What is important to notice about these energies is that they depend on the inverse of L squared. In other words, the smaller L is, the further apart the energy levels will be spaced. So quantum dots of smaller sizes will have a larger bandgap and quantized energies. However, changing the bandgap isn't a vast improvement over available technology, as it is still bound by the Shockley-Queisser limit. There are other ways quantum dots can be exploited to surpass this limit. The Shockley-Queisser limit is for a cell with a single p-n junction, so one way to surpass it is by layering materials. A material with a large bandgap can be layered on top, absorbing the high-energy photons and allowing lower-energy photons to simply pass through. The lower-energy photons can then be absorbed by the lower layers, reducing losses from photons being above or below the bandgap. However, actually fabricating a solar cell like this poses many challenges. To be grown on top of each other, materials need to have a similar lattice constant. As a result, the fabrication becomes complicated and expensive, and the increased efficiency is not enough to pay off in terms of the added expense. Quantum dots can help with this problem. They are suspended in solution, so there is no crystal lattice that needs to be matched. Films of quantum dots can simply be deposited on top of each other to create a multi-junction cell. Finding materials with optimal bandgaps is also easy because changing the size of the bandgap of a quantum dot is as simple as changing its size. Efficiency of a multi-junction solar cell can reach 50% for 2 layers with optimally chosen bandgaps. But design with quantum dots has not achieved such efficiencies yet. A recent 5-layer quantum dot solar cell reported an efficiency of 15.47%, which is still lower than the 20% efficiency of a single crystal silicon solar cell, which are standard in commercial use. The ease of fabrication could make quantum dots a cost-effective method of fabricating multi-junction solar cells, but there is plenty of research to be done before this concept is realized. Another way to enhance efficiency is to use hot carrier solar cells. As it travels to the metal contact, an electron with energy above the bandgap will lose this excess energy as heat. Decreasing the distance an electron has to travel could prevent this energy from being lost and improve absorption by the metal contact. To see the effects of hot carriers, the electron cannot travel more than a few nanometers to the contact. The quantum confinement in quantum dots also benefits a hot carrier solar cell. Quantum confinement slows the cooling of carriers, which will further prevent energy loss. This approach has mostly been demonstrated in concept, though. There is not a lot of work emphasizing the actual performance of a quantum dot solar cell using this structure. Most of the research in quantum dot solar cells uses different effects to achieve higher efficiency. It is still worth noting, though, as this hot carrier solar cell could be combined with other effects to make the most optimal solar cells. The last way in which quantum dots could improve efficiency is by generating multiple electron-hole pairs from one high-energy photon. In bulk materials, this process is very rare and only occurs for photons with energy much greater than the band gap, so it is often assumed to be negligible. However, in quantum dots, the discrete energy levels allow for more possible transitions, making this effect more pronounced. NREL did an experiment confirming the occurrence of multiple exciton generation in quantum dots, showing that up to 3 electrons could be created per one photon. The Shockley-Queisser limit assumes that only 1 electron is generated per photon, so by factoring in these effects, it is possible to achieve a theoretical efficiency of 65% with quantum dots. While this concept is promising conceptually, there aren't many demonstrations that have succeeded in enhancing efficiency with this route. The future of quantum dots looks very promising. Solar energy has seen rapid commercial growth, but it is widely recognized that there are improvements that need to be made before it can really command the energy market. There is extensive research into these third-generation solar cells, such as quantum dots, that promise to be cheaper and more efficient than current technology. The best reported efficiency for a quantum dot-based solar cell so far is only 16.5%. So future work would have to address bringing this number closer to the theoretical limits that have been discussed. Such low efficiencies may seem dismaying, but the efficiency has been rising steadily each year since quantum dot solar cells were first tested. Another challenge to be addressed is the toxicity of the materials. Many quantum dots are made out of toxic materials like lead or cadmium, while silicon is a very benign material. These toxic materials need to be carefully contained to prevent health risks, but it'd be preferential to not use them at all. Some research has looked into other materials, but so far non-toxic alternatives have lower efficiencies than their toxic counterparts. Fortunately, neither of these concerns have proven to be too big of an issue for quantum dots. They aren't commercially viable yet, but this hasn't stopped a few companies from beginning to market quantum dot solar cells. Despite the remaining challenges, quantum dots have the potential for immense improvements over the solar panels available today. Thank you for watching my presentation on quantum dot solar cells. I hope you learned a thing or two about how quantum dot solar cells work and why they could be a key technology in the future.